So just to review the continuous versus line spectrums. In a continuous, all wavelengths of visible light are represented, and this is observed with white light. Okay. That one right there. In a line spectrum, which is this, only certain wavelengths are represented. Okay. This is from an emission spectrum with discrete lights, and they are unique for every element, and they can be used to identify that element. The last one is an absorption spectrum, and this is when a source of white light is being filtered from a sample, and you can see the black lines that would correspond to the emission spectrum of the sample that's being filtered, or the element. And it's that one right there. I like this graphic because it shows you the difference between the continuous spectrum coming straight from the light source through a prism, being filtered through a sample of gas, that absorption spectrum, or from the excited gas itself, the emission spectrum. This is from the electrons being excited, jumping up in energy and level and down. Okay, Max Planck really did experiments so that we could determine how much energy is contained in a photon. So this E is the energy of a photon, that little packet of energy. Okay, and that's equal to Planck's constant times the frequency of the light. We're going to watch a little movie on the photoelectric effect. I need to find it.
In an evacuated tube, as shown here, is coated with an active metal. Electrons may be emitted from the metal when it is irradiated by light. This effect is called the photoelectric effect. Einstein explained the photoelectric effect by using Planck's concept of light as a stream of photons. When light of long wavelength impinges on the electrode, no electrons are emitted. Einstein proposed that this is so because the individual photons do not have sufficient energy to dislodge an electron from the attractive forces of the metal. Even when the light intensity is increased, there is no emission of electrons and no current flows. When light of shorter wavelength strikes the surface, electrons are emitted and are drawn to the anode. Thus, a current is seen to flow. Einstein proposed that the photons of shorter wavelength light impart sufficient energy to the electrons to enable them to escape from the metal. The kinetic energy of the electrons is the excess of that which they require to escape from the metal. When the intensity of the shorter wavelength light is increased, more electrons are emitted, and the observed current increases. However, the excess energy which the electrons possess remains the same. A higher intensity of light increases the number of electrons emitted, so the current increases. However, because each photon still imparts the same energy to each electron, the kinetic energies of the electrons remain the same. When light of still shorter wavelength is employed, the electrons are emitted from the metal with higher kinetic energy. This is so because the higher energy photons have imparted more energy to the electrons, and more kinetic energy remains after they escape from the metal.
Okay, so that's the photoelectric effect. And really what that goes is to further support this idea of light waves containing little packets of energy, those photons. And that energy is related to the frequency and hence the wavelength of that light. Okay, and this gives us a value for Planck's constant of 6.63 times 10 to the negative fourth joules second. So Bohr's idea of the atom was this orbital, okay, with set energy levels and electrons being able to jump up and back. Okay. But that model is kind of overtaken by one that is now called quantum or wave mechanics. And kind of like an orbit, the electrons can only exist in certain discrete orbits. Okay, they are restricted to this quantized energy state, meaning the different energy levels. They can't really be between an energy level, they have to be on an energy level. Schrodinger applied that idea of electrons behaving as a wave to the problem of electrons in atoms. He developed a wave equation, which is beyond the scope of this class, and wave functions. And those described an allowed energy state of an electron. And it's based on probability models in calculus. And then you have Heisenberg's uncertainty principle, which is because the electron is so small, we can't simultaneously define both the position and the momentum, because by putting the energy needed to determine the speed or the momentum and the position of an electron causes it to absorb energy and go hurtling off in unpredictable paths. So his uncertainty principle basically states you can either know the position of the electron or the speed, but you can't know both at the same time. And then that leads us into the idea of orbitals and sublevels and main energy levels as being probability volumes of where the electron is likely to be found.